Hello wonderful person, this is Anton, and what you're seeing right here is a kind of a digital representation of a typical asteroid in the solar system that astronomers have been studying for many decades. And while many decades ago, the overall view of these objects was that many of them were just these very large, boulder-like objects, kind of like something you would see in Star Wars or Star Trek. But then, approximately a decade ago, some of the close examinations of these objects, especially visitations by the Japanese and the American probes and the missions involving the Ryugu and Bennu asteroids, discovered that many of them, and possibly most of them, seem to actually not be single objects. And instead they represent a kind of a rubble collection, or a kind of a rubble pile that's made out of individual tiny rocks and a lot of dust that's then held together by gravity and possibly electrostatic forces. And that's actually something that became extremely important and very influential during the NASA's asteroid impact mission known as DART. We briefly discussed some of the discoveries in one of the videos in the description, but basically here one of the main discoveries was that the asteroid that NASA collided with was once again a rubble pile and not a single rock like you see right here. And as a result, this produced some extremely powerful emissions and basically created this. The entire asteroid fell apart and then reconstructed itself into a new shape, which was a pretty unusual but also a pretty interesting discovery. But today we're going to be discussing something that once again surprised everyone, because here we have something that's almost the opposite. Based on a recent discovery from a brand new observatory in Chile, scientists realized that sometimes some asteroids, even large asteroids, can actually be pretty strong. Because here they found at least one object that seems to be spinning extremely fast, and way faster than we've seen any asteroid spin. As a matter of fact, if this was any other asteroid, it would have already broken apart and would not exist. And so here this is a story of a newly discovered 2025 MN45, a space rock that is currently rewriting what we know about the internal strength of certain types of asteroids. And so here we're going to discuss how this asteroid was discovered, why its speed was once thought to be impossible for the object of its size, and what this tells us about the violent history of the solar system. And I guess let's start with the first. How was this discovered? And surprisingly here, the discovery did not come from a specialized asteroid hunting mission, and instead was actually a testing phase of the now famous Vera Rubin Observatory located in Chile. This observatory is equipped with a massive 3.2 gigapixel camera, referred to as LSST cam. And while during its first look program, when it was just testing the camera, this was between April and May of 2025, the telescope was actually focusing on the Virgo cluster of galaxies in order to test its sensitivity. And while looking at distant galaxies, it accidentally captured over 2100 asteroids that were moving in the foreground and were basically photobombing the galaxies. And even though astronomers initially thought they would find some asteroids, they did not expect to find 2100. And while among these asteroids was the object we're discussing today, 2025 MN45. Here's, by the way, where all of these asteroids are located in relation to Earth and the Sun. Although technically this has been seen before, with this image from 2017 showing us a single 175-second exposure from before. But it wasn't actually clear if this was an asteroid or something else entirely. So it was officially only confirmed in 2025. And in terms of what this is, it's actually not that unusual. This is a main belt asteroid orbiting the Sun between Mars and Jupiter, and is approximately 710 meters across, or about 0.44 miles in diameter. This is roughly between the asteroid Bennu and Ryugu, which is relatively common for these types of asteroids. But just to give you a sense of scale, that's twice the height of the Eiffel Tower. So yeah, if this hits the planet, it's most likely going to result in a massive explosion. This is what we usually call a city killer asteroid. Luckily for us, there's no danger from this at all. But until 2026, nobody thought that this object was unusual. But then, a team of astronomers led by Sarah Greenstreet started to look at the data again and noticed something very bizarre about this particular object when it comes to its reflections. Now here I guess let's briefly discuss how we usually study various asteroids. Normally when looking at comets or asteroids, their brightness actually goes up and down at least once every few hours. And that's because most of them basically spin. And because not all sides of the asteroid are the same, they will often produce a curve that resembles something like this. This is basically the rotation curve that normally repeats every time the asteroid completes one spin. And this is, by the way, how we know so much about various asteroids like the famous Oumuamua, whose luminosity curve was so extreme that it could only be explained if this was an extremely flat or extremely long object that was spinning as it was entering the solar system. And so basically this is something we see from pretty much all asteroids. But in this case, something wasn't adding up. Here, when the researchers looked at the rotation curves of all of these asteroids, most took hours or even days to complete one turn. But 2025 MN45 seemed to flash in brightness at a rate we've never seen before, and that at first was believed to be some kind of a mistake. Mistake because it just seemed to be kind of impossible. And so after analyzing the light curves, and by confirming this with additional teams, researchers confirmed that the asteroid completes a full rotation every 1.88 minutes, or every 113 seconds. And that's something we've never seen before. Just for a comparison, the previously visited asteroid Bennu takes approximately 4.3 hours per rotation, and Ryugu takes approximately 7.6 hours. Yet here we had something that spins every 120 seconds. And for astronomers studying asteroids, this was a huge deal. For one important reason, something referred to as the spin barrier. Something that only applies to larger asteroids that are at least 150 meters across. Now, just so that we're clear, scientists have actually seen these fast rotators that usually take a few minutes to spin, but all of them were pretty small, usually just a few meters across, and basically the size of a bus or something. But in this case, we're talking about something that's once again twice as big as the Eiffel Tower, and much larger than 150 meters that we believe to be a kind of a limit. And for these larger asteroids, the theoretical limit before the break apart was always believed to be approximately 2.2 hours. In other words, no large asteroid has ever been seen spinning, completing a single spin, in less than 2.2 hours. And so if this is a rubble pile asteroid, here the centrifugal force is just going to completely pull it apart, with all of the rocks escaping into space and becoming their own individual pieces. Yet this asteroid was rotating nearly 70 times faster than the limit, which suggested something very strange. So here, this definitely cannot be a rubble pile, because in order to survive this rotation, this asteroid has to have a significant cohesive strength. Or in terms of actual numbers, astronomers estimate it needs a strength of about 9 megapascals, which is roughly the same as your typical solid rock. And that of course implies that this object almost definitely is a single massive solid chunk, or maybe some kind of a massive boulder, and even more excitingly, possibly even a chunk of metal. But before we jump to conclusions and start making assumptions that maybe this is some kind of an alien probe or something, here there's something else I need to mention. This was not the only such object. This was definitely the record holder for its size, but it was not the only superfast rotator found in the study. Because here 19 asteroids were spinning much faster than the 2.2 hour barrier, with the researchers finding so many that they basically divided them into two separate groups. The super-fast rotators that were spinning in less than 2.2 hours, and the ultra-fast rotators whose spin was less than 5 minutes. And for these ultra-fast rotators, there were actually two more objects. Now I don't really have their images, but one of them was 2025 MJ71, and one of them was 2025 MK41. The first one was spinning every 1.92 minutes, and the second one was spinning every 3.78 minutes. So just a little bit slower, but not by much. Which once again challenges the rubble pile theory. Or essentially, a lot of these asteroids cannot be the collection of loose rock, and have to be individual pieces in order to spin so fast. Which is once again in contrast to the previous discoveries in regards to Ryugu and Bennu, where it was definitely confirmed that these are rubble piles. And so technically this is the first time in history that we've seen large rocks spin so extremely fast. And finding multiple such objects, with some of them almost as big as 1 kilometer across, basically suggests that a lot of these solid asteroids might be much more common than we previously thought. Because here this was only out of 2,000 asteroids, and in just one part of the night skies. But now we also have, I guess, a new question. So, how exactly did they get this way, and how did they form? And here, the leading explanation suggests that these are fragments from very dense cores of much larger parent bodies. So here we're talking about ancient planetesimals that were possibly destroyed by various collisions millions or even billions of years ago. And so some of them could actually be chunks of metal that used to be a core of some kind of a planetesimal. And so they were possibly born spinning so fast. But here we also have to remember that there is something referred to as the Europe effect. The very powerful effect from the sun that actually ends up accelerating the spin of the object, and even ends up pushing it just a little bit, which usually causes asteroids to slightly shift their orbits, but to also start spinning faster and faster until one day they either become two asteroids by splitting apart or possibly completely fall apart. And this is actually why in the solar system there are so many different binary asteroids. As a result of the Europe effect that basically makes them spin so fast, many asteroids just separate and become binaries. But here the pressure from the sunlight very likely sped up this asteroid for millions of years until it reached these extreme velocities. Which of course raises the next question: so exactly when will it actually fly apart or break apart if the Europe effect continuously acts on it? Right now there's no actual answer, but this is something that hopefully will be explored in future studies. Okay, cool. I mean, this is all interesting and stuff, but why exactly does this matter for us right here on the planet? Well, this all goes back to that DART mission once again. This once again challenges our understanding of planetary defense. Because here let's assume for a second that this city killer asteroid is actually on the way to collide with the planet in the next few years. Right now, based on this NASA mission, we know for a fact that we can actually redirect this asteroid by colliding into it. But in order for this mission to be successful, we have to know exactly what it's made out of. If this is a loose pile of rubble, just like with this mission, it's just going to completely fall apart and actually be redirected by much more than we anticipated. So here it's actually going to change the orbit much more dramatically. In contrast, if this is a solid piece of rock or even metal, it might not even budge that much. It might have some effect, but it just might not be enough. And so here breaking or moving a solid rock would be extremely difficult, and is definitely something that has to be considered if such an event ever happens. Then, at the same time, this discovery highlights the incredible potential of the Vera Rubin Observatory. And that's because after just 9 days of testing, a tremendous number of objects was discovered completely by accident, and even here the data was already incredible. But in late 2026, the telescope is going to start a 10-year-long project, observing everything every single night. And that means that we might discover up to 5 million new asteroids, with so many new objects discovered in a solar system that we never knew existed. And so astronomers are probably going to find thousands and thousands more of these strange, fast-spinning objects, which might help us discover an entirely new type of asteroids, but even help us map out the collisional history of the solar system and help us understand how everything here evolved. But also helping us understand how these objects seem to differ and what most of them seem to be made out of. But in summary, this asteroid 2025 MN45 right now definitely shattered everyone's expectations. This 700-meter wide, fast-spinning boulder seems to prove the existence of very strange asteroids, and asteroids that nobody imagined and nobody knew existed. But by the same time next year, we're most likely going to have quite a few more of these objects to discuss, and possibly even discover new moons in the solar system that were previously completely invisible. And if you'd like to find out more, subscribe and watch out for that next video. Until then, thank you for watching, come back tomorrow to learn something else, support this channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining a channel membership that grants you early access. You can also support this channel by buying a Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.